Hey folks, as we begin a unit about right triangles with trigonometry, we're going to study the Pythagorean theorem, and to introduce that, I'm going to show you a proof of the Pythagorean theorem that was patented by President James Garfield, who, as a matter of fact, is a member of my fraternity. That we're both alumni of the same fraternity, so pronounced Delta Upsilon. Fraternity founded on justice, but that's not the point. The point is, President Garfield has an awesome proof of the Pythagorean theorem. Now, this man was quite brilliant. Aside from being a mathematician, he could write simultaneously with both his left hand and right hand, one hand in English, the other hand in Latin. Too bad he was assassinated. Why? Because he believed in justice. A disgruntled dude that wanted a cabinet position, but anyway, that's not the point. So let's talk about right triangles. We've right triangles, we've talked about this before. They don't have sides, they have legs. So we're going to talk about a right triangle with leg A, a leg B, and a hypotenuse of C. Okay? Now what we're going to need for this proof of President Garfield is two of them. Okay? We're going to need two right triangles. So we have two right triangles. Now we're going to need a couple other things. We're going to need to know the formula for the area of a triangle, any triangle, and you should know that the formula of the area of any triangle is 1/2 times the base times the height. The other thing we're going to need is the area of a trapezoid, any trapezoid. And the area of any trapezoid is 1/2 the average of the bases times the height. So no matter what base you have, if you add them together and divide by 2, you have the average of the bases, and in any trapezoid you have the height. So we're going to need that information to begin a proof of the Pythagorean theorem. Now, what President Garfield did was decide to begin with a right triangle with legs A and B and a hypotenuse of C, and he's going to copy that right triangle and reposition it alongside of the other right triangle. So he's going to reposition it to make a shape that looks like this. Now, what shape are we looking at? As a matter of fact, we're looking at a trapezoid. What? Mr. Katz, are you for real? Yes, this is a trapezoid, because maybe this will help if I spin it around a little bit so you don't have gravity mess with you. We have a trapezoid. Two parallel lines, right? 90 degrees, parallel lines, and a quadrilateral. Okay? So we have a trapezoid. Now, what we also have is 3 triangles. Wait, what? Yes, 3 triangles. We have the 2 triangles that we have put side to side, and we have a 3rd triangle that is established here. Now, this 3rd triangle is also a right triangle, and that's an important concept because in a right triangle, we are given a base and a height. Okay? In a right triangle, we have a base and a height. In a right triangle, we have a base and a height, and in a right triangle, we have a base and a height. Okay, now, it's important to establish that this 3rd triangle is a right triangle. Now, how do we know that? Because the other 2 angles are supplementary. The other 2 angles are complementary, and so the leftover angle in that triangle is going to be 90 degrees. So therefore, everything adds up to 180. So, President Garfield decides what we're going to do is talk about the area of the big trapezoid that we have formed being equal to the area of each of the 3 triangles. So we find the area of this triangle, the area of this triangle, the area of this triangle, that would equal the area of the trapezoid. Okay, so that is the setup. Now, how is that going to work? How are we going to knock this out? Well, we're going to work with what we've established. What is the area of a trapezoid? The area of a trapezoid is the average of the 2 bases. In this case, B, length B is base 1, A, length A is base 2. And so we add A plus B, but we divide it by 2 so we can find the height. Okay, so that is the average of the bases, b1 plus b2 divided by 2. And then how do we find the area of the trapezoid? We have the average of the two bases times the height. Now, what is the height of this shape? Okay, the height of this trapezoid is from here to here. That is segment B plus segment A. So the height is, funny enough, A plus B. So the area of the trapezoid is this. Our A plus B divided by 2 times the height, A plus B. That's the area of the trapezoid. And what is that equal to? Again, that is equal to the area of each of these triangles. Okay? So what's the area of one triangle? We have 1/2 the base times the height. 1/2 of A times B. Okay, so we're going to establish, well, in this bottom triangle, 1/2 of A times B. In the top triangle, again, 1/2 A times B. And the third triangle, remember the one that's going to be important to establish that right angle? It's 1/2 of C times C. Now, what is C times C? Hopefully you know it is C squared. So this is our setup. The area of the big trapezoid being equal to the area of the three triangles. Now what we're going to do is some magical algebra. Yes! So let's take a look at the left side. We have A times B times A times B, also known as, or A plus B times A plus B, also known as A plus B squared, over 2. That's what this is. And that's going to be equal to, now, what's 1/2 AB plus half AB? That's a whole AB. So that is just AB. And then we're going to add to it 1/2 of C squared. Okay, well, that's interesting. That's an algebraic fact. We've done nothing wrong. But now we look at this, and what can we do? Well, we have a fraction here and a fraction here. I don't know if you like working with fractions and equations. I certainly don't. So what we're going to do is then multiply both sides by 2, by the denominator. So if we clear the fraction, we can multiply the entire thing by 2. So that means every little piece will be multiplied by 2. So what happens with those pieces that have a denominator of 2? The denominator cancels. Okay, so on the left-hand side, we are left with A plus B squared. On the right-hand side, now we had an AB here, but we were multiplying it by 2. So it is now 2AB. We had a 1/2 C squared, but we're multiplying by 2. Remember what that 2 does? It cancels out the 2 in the denominator, leaving us with only C squared. So that is currently where we are at. So we have done nothing wrong. Everything is factual. Now what we can do is work on this A plus B times A plus B. How does that work? How does that work? Well, A plus B squared. A plus B times A plus B. All right, so we use the distributive property in binomials, so it's A squared plus AB plus AB plus B squared. Okay, so that's A plus B times A plus B. That will be equal to 2AB plus C squared. We leave that side there. Okay, so that's all set up now. So what's next? On the left-hand side, we can see that we have an AB plus an AB. How many ABs do we have? We have 2 of them. So A squared plus 2 of the ABs plus B squared would be equal to, on the right-hand side, 2AB plus C squared. Right? So far, so good? Great. So now, we've done nothing wrong. Everything is kosher. Is there anything else we can do? Well, if you notice what's happening, we have a 2AB on the left-hand side and a 2AB on the right-hand side. You know what we could do? We could subtract 2AB from both sides. So we subtract 2AB from both sides. And some magic occurs. Something that might look familiar happens. We are left with A squared, that cancels, plus B squared, equaling, that cancels, C squared. Now we have a proof of the Pythagorean theorem by President James Garfield. Now, one thing I want to leave you with, I don't want you to call this A squared plus B squared equals squared. I want to make sure that you know what this means. It means the following, and so please make sure you know your vocabulary so we can use good vocabulary. what the Pythagorean theorem states is that the sum of the squares of the legs of a right triangle, the sum of the squares of the legs of a right triangle is equal to the square of the hypotenuse. The sum of the squares of the legs is equal to the square of the hypotenuse. Okay, so please recall that. Sum square legs equal square hypotenuse. And that, my friends, is the Pythagorean theorem shown to you by my fraternity brother, President James Garfield. Thank you very much.